Test, test, test. Test, test. 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 Alright, I will start with your questions first. I'll give like 5 or so minutes to have people post questions or email me or whatever, and I'll use that as a starting point. So go ahead and ask. If there's no questions in the next like 10 minutes or so, I'll just start doing proofs. All right. 1 and 2, and actually 3 and 4 as well. Those are both inductive reasoning, which is what we went over at the very start of the chapter. So inductive reasoning is taking a pattern and expanding what you know about it to further out iterations, right? So number 1 starts in bottom left-hand corner, then it goes to bottom right, then it goes to top right, then it goes to top left. So this little circle is moving clockwise around the box. So for number 1, the next pattern would be like this. Pick a proof, Devin. I'm not sure what proof you're talking about. Which page is it and what number is it? All right. 1 second. So I'm just going to make one up. All right, so if we have a truth table that's totally blank, you always start it in the following pattern. So true, true, and then true, false, false, true, and false, false. So if I gave you this table, you would have to fill in all of this, and you would start with this pattern. All right, so not P in this case because P is true, not P is false. Not P in this case because P is true again, this is still false. P is false here, so not P is true, and same down here. So this squiggly line, that's the not. This V, that's or. And this upside down V is and. Alright, so everything else is just taking this information and plugging it into these statements. So not P or Q. Not P in this case is false. So false or Q, which is true. Because one of these are true, the entire statement is true. Okay, again, not P is false. Q is also false. Because both of these are false, this statement is false. Down here, not P is true, and Q is also true, so we have true or true. Because one of these is true, the statement is also true. And then down here, we have not P is true, and Q is false. Again, because one of these is true, this entire statement is true. And then the last column, P is true, and not P or Q is also true. So we have true and true. Because both of these are true, this entire statement is true. Because in this second column, because not P or Q is false, this entire thing has to be false because both have to be true. P in the third column is false, so that means this is false. And P in the fourth column is also false, which means this entire thing is false too. So that's a really quick example of this, but it works the same way. It always works in this pattern. So true, 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 false, false, true, false, false. And then everything else is just filling in using those statements. All right, 10 on page 2. I'm guessing you mean this one right here, right? Or are you talking about the actual like book test? Got it. All right. So our first statement is always just the given. So VW, and actually I'm going to redraw this first just so I can. So first statement is always just restate what's given. So VW, and actually I'm going to use measures. So VW is equal to RS, and XY is equal to RS as well. And we want to prove that Vx is equal to Wy. In order to do this, what I would do is to get equations for the left-hand side of this equation and the right-hand side of this equation. Alright, so my second statement would be to get an equation for Vx and an equation for Wy. So Vx is equal to Vw plus Wx. And we can do that because of segment addition. Wy is equal to Wx plus Xy. And again, that's the same reason. I count those two as the same step. You can do it as a third, but it's the same reason. Now, because Vw is equal to Rs, and Xy is equal to Rs, we can do a little bit of substitution. Alright, so I'm going to rewrite Vx. I do just so I can talk about it with you all. It's not a bad habit to get into. So we can rewrite Vx as Vw, which is really just Rs plus Wx. And we can rewrite Wy as Wx plus Rs. So in this step, we use substitution. And then because Vx is equal to Rs plus Wx, and Wy is also equal to Rs plus Wx, Vx will equal Wy by the transitive property. You could also use substitution here, but this works. Are there any questions about that proof? Yeah, so step 3. We can rewrite Vw as Rs. So anywhere we see a Vw, we can rewrite it as Rs. Alright, so in step 2, we see Vw, and we rewrote that as Rs. We can also rewrite Xy as Rs. And in the second equation, we have an xy down here, so we can rewrite that as Rs. So that's why that first given step is very important. We know that VW is RS and we know that XY is RS. So anywhere we see those two, we can rewrite them as RS. You can replace VW for RS and you can replace XY with RS. So we're not really replacing entire lines, we're just substituting for what VW is also equal to and XY is also equal to. So, and actually, I'm going to do something a little bit different that might make this make a little bit more sense. So in this drawing, the green drawing on the right, instead of using like segment notation, I'm going to make the distance, each of these distances a different variable. All right. So the distance on the left, that's A. The distance in the middle, that's B. The distance on the right, that's C. And then this smaller one that's detached is D. All right. So I'm going to rewrite this proof using that. All right. So step one, we know that A is equal to D. And we also know that C is equal to D. And that's given. And we're trying to prove that A plus B is equal to B plus C. Alright, so step two would be to get an equation for A plus B. We kind of already have that. So these are just equal to themselves, so I'm not going to rewrite that. This is our segment addition. Not really, because we're not using segments, but we're using distances. Step three would be to substitute A for D and C for D. So then we would get D plus B and B plus D, which again is just substitution. And then our fourth step, D plus B is equal to B plus D. I think that's symmetric, or reflexive, rather. But instead of using all this terminology, we just simplified it to certain distances. I hope that makes a little bit more sense. That being said, I don't want you to split things up like this, but this is in order to kind of help with everything in red. Does that make sense, or does that... Okay. If there's no questions on this one, what others can I do to help? All right, 27. Um, it gives us a couple of angles. I'm going to focus on the measure of angle NOP and the measure of angle SRP. So NOP is right here, and SRP is right here. And I'm going to draw this in just so I can look at it without having to constantly go back to this given thing. All right, and we're trying to prove that angle POR is congruent to PRO. So again, the first thing to do is to just state what's given. All right, and we're given that the measure of NOP is congruent to SRP, NOP is complementary to POR, and SRP is also complementary to PRO. Now, we could actually do this in like 2 steps. So I'm gonna rewrite this as what complementary's definition actually is. So what this means is that the measure of angle NOP plus the measure of angle POR is equal to 90 degrees. And that is just the definition of complementary angles. I'm also going to rewrite that second line. It's the measure of angle SRP plus the measure of angle PRO is also equal to 90 for the same reason. And then we can do some substituting. So because NOP is congruent to SRP, we can replace them. All right, so we're going to rewrite this top line as the measure of angle SRP plus the measure of angle POR is equal to 90 degrees. And we can do that because of substitution. Now, we can actually use one of the last theorems we went over in class to say that angle POR is equal or is congruent to PRO because if 2 angles are complementary to the same angle, then those 2 angles are congruent. So this theorem was called Congruent Complements. And I'll try and walk over why that's true. All right. So in both of these equations, I'm going to try and find a different color. In both of these equations, we have the measure of SRP. All right. So the measure of SRP plus something else will equal 90. That's this green equation. And this bottom equation, the measure of angle SRP plus the measure of something else is also equal to 90. So what this boils down to is that the measure of angle SRP plus some angle is equal to 90. All right, so that's the top one. And the bottom one, the measure of angle SRP plus a different angle is also equal to 90. So really, because they're both equal to 90 by the transitive property, they are equal to each other. And because we have the measure of angle SRP on both sides, they cancel, and we're left that x is equal to y. And in that case, the x is PRO, and the y is POR. So you can go through that in the proof, but we went over a theorem to save you all of these steps. And that theorem is this congruent complements theorem. So those are there to help you. Those are there to make these things at least a little bit simpler. Are there any questions over that? I'm going to scroll up just a little bit so people can see it. And I might make it all smaller. All right, if there's no questions on 27, I'll do 29. All right, 29. So 29 is, we're given that Vs is equal to Vr, and we're given that Wt, the center line, bisects Vr and Vs. And we're trying to find the perimeter of this entire thing. Okay, so I'm gonna, this is more of an evaluate than a proof, but we can do it in proof format. I'm gonna just do a squiggly line so I don't have to copy everything that's given. It's all right there. Step 2 would be to find equations for all of these lines. So Vs, and there's a lot of different ways you can do this, but this is how I would do it. Vs is equal to Vt plus Ts, and Vr is equal to Vw plus Wr, and that is segment addition. We also know that Wt bisects Vs and Vr, which means that Vw, I'll start Vt. Vt is equal to Ts, and Vw is equal to Wr. And that is just the definition of bisection. So because this middle segment splits these lines directly in half, Vw is equal to Wr and Vt is equal to Ts. Then we have to start substituting a little bit. So we could actually, from step 2 and step 3, Vs is equal to Vt, or rather, let's do this. Because we know Vs is equal to Vr, we know that Vt plus Ts is equal to Vw plus Wr. And that's just substitution. So we are substituting Vs for what it actually is, and Vr for what it actually is. Now, we also know from step 3 that Vw, I guess we'll do this, Vt is equal to Ts, therefore 2x is also equal to Ts. And that would also be substitution. Chances are you're not going to get a problem like this, because this is a little bit different than what I'm trying to get at. But Ts is also equal to 2x, so we're going to put that up here. And then from there, we can actually start to substitute things in and find a total perimeter. So because Wr, well, no, we gotta do this first. All right. Because of step 4, we know that each of these smaller parts are equal to each other. All right, I'm gonna skip explaining all of that, but because of the definition of bisection and step 4, we know that each of these segments are equal to one another. So VW is equal to VT is equal to TS and is equal to WR. And there's a lot of substitution going on there. And segment addition alright, and from there we can find what X is, and then we can find what Y is. Sorry, I know this is confusing. I hadn't done this one yet. So because all these things are equal, I'm going to start with TS and WR. Because TS is equal to WR, we know that X plus 4 is equal to 2X. And again, this is all just like substitution. And because of that, X will equal 4. So then, because TS is equal to 4, that means that VT is equal to 4. Again, that's substitution. And then we need to find what Y is. So VW is equal to VT. So that means Y plus 5 is equal to 4. Which means that Y is equal to negative 1. Which means that VW is also equal to 4. So the length of these two legs are both 16 units long. So that's a total of 32. But I screwed up somewhere. All right, but that's okay. I'm not going to redo this because this isn't a problem that I'm going to make you do. But that same logic, I don't know where I screwed up, but this same logic is what I'm kind of testing. No, you're not going to have to find perimeter of anything. And if you do, it's not going to be this long. So let's leave that there. This is the logic, but we can't get, because I found that Y is negative 1, we can't have a side length that's equal to negative 6. It doesn't really work that way. At least not in Euclidean. But are there any other questions? So sorry I didn't answer that necessarily, but it's the same logic. Right. Give me 1 second to get that. All right. Truth tables. This is directly from IXL. And the proof that I give you will probably be more like the one I did before. So it'll probably more look like this, where I just give you a blank table and you have to fill out everything. But this is a good exercise. All right. So remember that caret is and statement and V is or statement. All right. So in this case, S and R, both of those things have to be true for that box to be true. All right. So this has to be true because both. Whoop, nope, they're not. So we're looking at R and S. R is false, S is true. They are not both true, so this statement is false. And then the negation of that would be true. And then we're looking at Q, or this not statement. Both of those things are true, which automatically makes this true. In this case, S and R for this column. All right, we're looking at R and S for this first box. Both of those things are not true, so this is a false statement. The negation of that is true. And then we have true or false. One of those things is true, so this statement is true. In this table, for this top left-hand box, we're looking at R and S. This is an or statement, so only one of those things has to be true. So because R is true, this entire statement is true. The negation of that, so the negation of truth is false. And then we're looking at not S or R. So R is true, which automatically makes this statement true. Again, S or R have to be true in this case. S is true, which makes the statement true. The negation of that is false. And then we're looking at R or this. Both of those things are false, so this is a false statement. S or R in this bottom case is false because one of them is not true. The negation of that is true. And because that negation is true, this entire statement is true. we could do more proofs. But yes, we can go over number 10 on chapter 2 first. All right, a couple things in number 10. So remember that a syllogism is if A then B, and if B then C. That means that if A, then C. So if Margaret or if Margot goes to college, then she will major in chemistry. If Margot majors in chemistry, then she will need to buy a lab manual. So if she goes to college, she will take chemistry. If she takes chem, then she needs a lab manual. So because she's taking chem, that's like the linking statement. So our answer is if she goes to college, then she will need a lab manual. Conditional statements. So if our original conditional statement is if A, then B, our converse is that reversed. So if B, then A. Our inverse is if not A, then not B. And our contrapositive is the inverse of the converse. So if not B, then not A. If both of these things are true, so if the original and the converse are true, that means you have a biconditional statement. Which looks like this. So A, if and only if B. So it works both ways. So, for example, and this is one I'm just going to make up. If our original statement says if two lines are parallel, then they don't touch, or then they don't intersect. The converse of that would be if two lines don't intersect, then they are parallel. The inverse would be if two lines are not parallel, then they do intersect. And the contrapositive would be if two lines intersect, then they are not parallel. Now, because the original is true and the converse is true, that means we have a biconditional statement. So we can rewrite this again, because both are true, we can rewrite it as two lines are parallel if and only if they do not intersect. So I'll just say if we can be done here in a minute. If there are any questions, I can go over them. But this goes over pretty much everything, and then I'm going to expect you to know. All right, with the exception of number 29 as a proof. I think that's a little bit out of reach right now. The simpler, like 4 or 5 step proofs, those are reasonable. So number 27 is reasonable. Number 19 is reasonable. Those first 4 or 5 that we did in class, those are reasonable. So those things I would expect you to know. Truth tables, conditional statements, inductive reasoning, which really shouldn't be that hard. So questions 1 through 4, just being able to find a pattern and then expand on that. And then that's really about it. The only caveat is that proofs require a lot of background knowledge. So you need to know the postulates, you need to know the formulas, you need to know the theorems. All those things are mandatory almost, and you don't need to know the number of them or the exact name, but you need to be able to state what they do. So I'm gonna leave this open for the next like 5 or so minutes, and if you have questions, I'll answer them. But after that, if there are no questions, we'll end this here. Okay, I will end this here. Again, this is just like a preliminary review. We'll get the practice test next class. I'll have another one of these, and we can be a little bit more specific about what we're asking. Again, those super, super long proofs I'm not going to expect you to do. But I will expect you to do those, 4 or 5 step proofs. The way we've been doing it in class and the way I did it for these couple of questions. So 27 and number 10. I think those are about the difficulty I would expect you to be able to do. So if you have any questions, please come and see me. Even if you don't have class that day, I'm usually always available during activity period. Or just send me an email and I can be available. All right, so I will end it here. Thank you for questions. Again, you can always email me as well.